If I told you that, well, depending on what part of the wave you're actually measuring, you might get not just one, but maybe two completely different answers. It's one of those sort of hidden truths in physics. And once you get it, it really changes how you see things.
That's exactly the mystery we're diving into today. We're taking a deep dive into these two fundamental, but yeah, often confusing concepts, phase velocity and group velocity.
Right.
Our goal really is to pull back the curtain a bit, clarify how they behave differently, and understand their impact. Because it's huge, from light hitting your eyes, sound reaching your ears, all the way to, well, the very fabric of matter itself.
And to help us navigate this, we've drawn from a really rich set of sources. We've got foundational physics texts, some cutting-edge engineering reports, practical discussions, even detailed experimental data.
Yeah, quite a stack.
So the aim is for you to walk away with a pretty comprehensive and actually surprisingly practical understanding of these two speeds.
Let's do it.
Okay, so let's start at the beginning. We all have a basic idea of a wave, right? A propagating disturbance, like ripples on a pond or light moving through space.
Sure.
But when we talk about its speed, what are we actually measuring?
Well, the first speed we probably need to wrap our heads around is phase velocity. We usually just call it VEEP.
Got it.
Think of it as the speed of a single identifiable point on the wave, like one specific crest or maybe one specific trough as it moves through whatever medium it's in.
Okay, so like if you're watching ocean waves roll in and you just pick one single crest.
Exactly. You pick that one crest and you just track its movement. The speed of that individual point moving along, that's the phase velocity.
Okay, so you're literally pinpointing and watching one specific bit of the wave go by.
Yeah.
If I wanted to calculate that, what would I need? Is there a formula?
Yeah, there is. If you're tracking that single crest, you'd basically measure how far it travels in a set time. Mathematically, phase velocity is the wave's angular frequency, omega, divided by its wave number, k. So VP equals omega over k.
Okay.
Or you can think about it another way. It's the wavelength, lambda, divided by the time period, t, which is the time for one full wave cycle. So VP equals lambda over t. Same thing.
That makes sense for just tracking one point, but then there's this other concept, group velocity. And this is where I think things get really interesting.
They really do, because group velocity, or V, it's different. It's the speed of the overall shape of a group of waves.
The shape.
Yeah, think of it like a wave packet, or sometimes called an envelope.
Yeah.
It's not about one crest anymore. It's about the speed of the whole bunch, the whole package moving together.
Oh, okay.
And here's the crucial bit. Group velocity is generally the speed at which information or energy is actually carried by the wave.
Right. So if I'm sending, say, a Wi-Fi signal from my router, that little pulse of data, the actual information, the data packet itself, isn't traveling at the speed of one tiny peak inside that pulse.
No.
But rather the speed of the entire message that the pulse represents.
Precisely. That's the group velocity carrying the message.
That is.
Yeah.
That's a mind-bending distinction right there.
It is. And there's a really great analogy from one of our sources that helps picture this. Imagine you're watching an airplane propeller spinning.
Okay.
The actual speed of the propeller blades moving through the air doing work, that's like the group velocity. It's the physical movement.
The real speed.
But now imagine filming that propeller with a camera that has a fixed frame rate. Depending on that frame rate, the propeller might look like it's spinning backward, or maybe really slowly forward, or even faster than it really is.
Yeah, you see that sometimes in videos. The wagon wheel effect.
Exactly. What the camera sees, that apparent motion, the illusion that's like the phase velocity, the physical thing carrying energy, the propeller, is Vg. The optical illusion you might see is V.
Wow. Okay, that's a brilliant analogy. It really clarifies the difference between the physical reality and just the pattern.
Yeah.
So, okay, for those of us who like the nuts and bolts, what's the math behind this? How are VEEP and VG actually connected?
Well, the neat thing is there's a direct mathematical link. It's VG equals VP plus K, dVP dk.
Okay, let's unpack that. VG equals VP plus K times dVP dk.
Right. And that last bit, the derivative term dVP dk, that's the key. It basically tells you how much the phase velocity itself changes when the wave number k, or you can think of it as the frequency, changes.
So it's all about whether the phase speed stays the same for all frequencies or not.
Exactly. And that leads us straight into this really important concept called dispersion.
Dispersion, right.
Dispersion is just the name for this phenomenon, where the phase velocity of a wave depends on its frequency or wavelength.
So different colors of light or different musical notes might travel at slightly different speeds through the same stuff.
Precisely. In a dispersive medium, they do.
So like, if you're at a huge concert, way at the back, could the bass notes theoretically arrive a tiny bit later than the high notes because of dispersion in the air?
Over very long distances, and if the air were significantly dispersive for sound, yes, that's the kind of effect you could get. It's usually subtle in air, but the principle holds.
Okay, so what about when that doesn't happen? When Veep doesn't depend on frequency?
Well, that's what we call a non-dispersive medium. In that case, that dV/pdk term is just zero.
Because the phase velocity doesn't change with k.
Right. And if dV/pdk is zero, then the equation just becomes Vg equals Vp. They're equal.
Simple enough. Any examples?
The classic example is light traveling in a perfect vacuum. All frequencies, all colors travel at the same speed, c. So in a vacuum, both the phase velocity and the group velocity of light are equal to c.
But most materials aren't a vacuum. Most things are messier, right? So we usually have dispersive media.
Absolutely. In most real-world materials, glass, water, air to some extent, optical fibers, that dV/pdk term is not zero, so Vp and Vg will be different.
And that's why things happen like light pulses spreading out in optical fibers, because the different frequency components are traveling at different speeds.
Exactly right. The different components get separated, and the overall pulse, the group, spreads out.
Now, I heard there are even different types of dispersion. Something called anomalous dispersion sounds, well, anomalous.
Yes. There's normal dispersion, which is usually what happens. Longer wavelengths travel faster than shorter wavelengths. Think of the prism. Red light, longer wavelength, bends less because it travels slightly faster in the glass than blue light, shorter wavelength.
Okay, so red faster than blue. Normal.
In that case, the group velocity ends up being smaller than the phase velocity. Vg is less than V.
Got it. And anomalous.
Anomalous dispersion is the opposite. Longer wavelengths travel slower than shorter ones. This typically happens near frequencies where the material strongly absorbs the wave, like around a resonance.
Okay, weird.
And here's where it gets really wild. In anomalous dispersion, the group velocity can actually be larger than the phase velocity. Vg is greater than Veep. And in some very specific engineered situations, Vg can even become negative.
Negative, like the pulse travels backward.
Effectively, yes. The peak of the pulse envelope can appear to exit a medium before it even enters. It's not violating causality, it's a complex wave-shaping effect. But Vg can indeed be negative or even faster than light in these engineered cases.
Okay, that brings me to the really mind-bending part. You mentioned V can be faster than light in some cases, but I also read that phase velocity can exceed the speed of light c, even in relatively normal situations. Doesn't that, like, break physics, break relativity?
It sounds like it should, right? But no, it actually doesn't violate special relativity.
Why not?
Because, and this is the absolute crucial point, phase velocity does not transfer information or energy.
Back to the propeller analogy. The illusion can be faster, but the propeller isn't actually moving faster than light.
Precisely. Vp is just the speed of a point of constant phase. It's a mathematical point, not a physical object or signal carrying information. Think of it like a wave crest hitting a beach at an angle. The point where the crest touches the sand can sweep along the beach faster than the wave itself is moving forward, potentially even faster than c, but nothing physical is moving along the beach at that speed.
So Einstein is safe.
Einstein is safe. Relativity is concerned with the speed limit for information and energy transfer, and that speed
is the group velocity.
Exactly. The group velocity, Vg, is the speed at which the information or the energy packet travels. And that speed is always less than or equal to the speed of light in vacuum. See, no exceptions found.
Okay, that makes sense. That's why the speed of my internet signal in a fiber optic cable is limited by group velocity.
Right.
Not by some potentially superluminal phase velocity of the light waves inside. It's the data packet speed that matters.
Couldn't have said it better myself.
Okay, so this naturally leads to the question, what causes these velocities to be what they are? What factors influence them?
Well, the biggest factor by far is the medium itself, the stuff the wave is traveling through.
Right.
Take light. When light goes from air into glass or water, we see it bend, right? Refraction. That happens because the light waves interact with the atoms in the material.
They sort of get absorbed and re-emitted.
Yeah, you can think of it like that. There's a slight delay, a momentary hold during that interaction. The net effect is that the overall propagation speed of the phase changes, it slows down. That change in phase velocity is what causes refraction.
And for sound waves, it's different properties of the medium, like density or stiffness.
Exactly. Sound travels faster in solids than liquids or gases generally because the particles are closer together and the material is stiffer, more elastic. The medium's density and elasticity are key for sound speed.
What about other waves, like in electronics?
Sure, like electromagnetic waves moving through a conductor, like a wire. The wave's electric field makes charges move, creating currents. Those currents create their own magnetic fields, which then interact back with the wave, changing its phase velocity. It's all about the wave-medium interaction.
And of course, as we talked about with dispersion, the wave's own frequency or wavelength matters too, especially in those dispersive media.
Absolutely. Frequency is a huge factor in dispersive materials. And don't forget environmental factors like temperature. Temperature changes the density and elasticity of air, for instance, which changes the speed of sound.
Right, sound travels faster on a hot day.
So it's a combination. The medium, the wave's own properties like frequency, and sometimes the environment.
So let's talk applications. How does understanding all this actually get used? I mean, you mentioned optics. My glasses.
Your glasses are a perfect example. Photonics and optics rely completely on understanding VEEP and VG. Refraction, how lenses focus light, that's directly tied to changes in phase velocity as light enters the lens material.
And dispersion.
Dispersion explains why prisms create rainbows. Different colors, frequencies, have different phase velocities in the glass, so they bend differently and separate out. It's also crucial for designing optical fibers to minimize pulse spreading over long distances. And the fundamental property we use in all optical design, the refractive index N.
Yeah.
That's literally defined as the speed of light in vacuum C divided by the phase velocity Vp in the material. So N, NC, Vp. It's built right in.
Wow. Okay, and it gets even stranger in quantum mechanics, right? With particles acting like waves.
Oh, yeah. Quantum mechanics has matter waves associated with particles like electrons. And here's something really neat. The group velocity of an electron's matter wave turns out to be exactly equal to the actual classical speed of the electron particle itself.
That feels satisfying, like it connects the wave picture back to the particle reality.
It does. It feels right. But the phase velocity of those matter waves, that can give you some really weird results depending on how you define the energy involved. Sometimes it's half the particle speed. Sometimes it's faster than light if you include rest mass energy.
So the phase velocity is more abstract.
Yeah.
Less physically direct for matter waves.
Exactly. It highlights again that phase is more about the wave pattern itself, while group velocity connects to the physical transport, in this case, the particle's motion.
Okay, let's shift from the very small to the very large. What about using this for something like seismic exploration, looking underground?
Oh, absolutely vital there. Geophysicists use seismic waves, basically sound waves traveling through rock, to map out what's underground. Understanding phase and group velocity helps them characterize different rock layers, especially if the rock is anisotropic, meaning its properties change with direction.
How do they measure these velocities?
They measure the travel times of waves reflected or refracted off different layers to figure out the elastic stiffness coefficients, basically, how stiff the rock is in different directions. This tells them about the rock type, maybe if there's oil or gas trapped there.
So, in practice, out in the field setting up sensors, which velocity is easier to get a good measurement of, VP or VG?
Well, the sources we looked at were pretty clear on this. Group velocity measurements are generally considered more straightforward and reasonably accurate.
Easier. Why?
Apparently, they're less sensitive to the size of the sensors, the transducers you use. Even with relatively large sensors, if you measure the travel time using the distance between the edges of the source and receiver, you get a pretty good group velocity measurement. That makes it practical for real field data.
Okay, so VG is practical. What about VEEP then?
Phase velocity measurements are described as much more problematic.
Problematic how?
They often require specialized setups, like sources at different depths, and they are apparently very sensitive to the sensor size. Ideally, you need tiny point-like sensors. If your sensors are too big, they can distort the wavefront you're trying to measure, leading to potentially large errors.
Huh. So even though phase velocity might have these neat, exact theoretical links to the material properties,
Right.
in the real world of messy data and imperfect equipment, group velocity measurements often win out because they're just more robust and reliable.
Exactly. The sources suggest group velocity offers a definite advantage for practical seismic work because of its accuracy and robustness compared to the more error-prone phase velocity methods. It's a classic theory versus practice trade-off.
Fascinating. And just to bring it full circle back to everyday things, that refractive index you mentioned, the one based on phase velocity.
Yeah, NT-CVP.
It really is everywhere, isn't it?
It really is. Eyeglasses, camera lenses, microscopes, telescopes, all designed using refractive indices. Fiber optics rely on total internal reflection, which depends on refractive index differences. Even things like testing the sugar content in juice or identifying gemstones often involve measuring the refractive index. It's one of those fundamental properties rooted in phase velocity that shapes how we interact with light all the time.
So it really boils down to this. Phase velocity tells you how fast a single point on the wave pattern moves, and it can do some surprising things, even seem to break the light speed barrier sometimes.
But it's just the pattern.
Right. But it's the group velocity that tells you how fast the actual stuff, the energy, the information, the signal, is moving. And that speed always respects the universal speed limit.
That's the core takeaway. One describes the pattern, the other describes the transport.
So thinking about all this, what does it mean for you listening right now? Consider this really intricate dance happening inside every wave, where individual parts might be moving at one speed, maybe even faster than light, while the actual message or energy follows a completely different, much stricter rule. How profoundly do these subtle differences, Veep versus Veed, influence everything? From the technology that brings you this deep dive right now via the internet, to the very nature of quantum particles that make up reality, it makes you wonder, what other hidden speeds or hidden rules might be governing the world around us, just waiting for us to figure them out?